Section 3.2, polynomial functions and their graphs. In the last section, we studied quadratic functions, and the graph there was a parabola. Well, quadratic function is also a polynomial function. So we just studied in 3.1 a very specialized case of a polynomial functions. Quadratics are polynomials. But now, being a little more general, let n be a non-negative integer and a sub n minus 1, a sub 2, a sub 1, a sub 0 be real numbers with a sub n not 0. Then the function defined by all of that, I'm not going to read it all, but all of that is called a polynomial function of degree n. The number a sub n, the coefficient of the variable to the highest power, is called the leading coefficient. Now, what this is trying to tell us is, right here, let n be a non-negative integer. So that means 0, 1, 2, 3, 4, 5, 6, 7, that sort of thing. That my exponents, n minus 1, n minus 2, non-negative integers, my exponents are 0, 1, 2, 3, 4, numbers like that. The highest exponent is called the degree, and the coefficient on there of the degree term is called the leading coefficient. Then it's all summarized here. This means that a polynomial number has only whole number exponents, 0, 1, 2, 3, 4, so on. There are no negative or fractional exponents, no variables and denominators or radical. The degree of the polynomial is the highest exponent. So something is a polynomial when it has only whole number exponents, which then really means that you have no negative or fractional exponents, no variables in denominators or radicals. So looking at this first guy, determine whether the function is a polynomial. If it is, state its degree. If it's not, tell why not. So it's all about the variables and their exponents. I need to have the exponents be only whole numbers, 0, 1, 2, 3, 4, 5, 6, so on, and no variables and radicals or denominators. And so this first guy here is a polynomial, and I am trying to trick you here. Square root of 2 is a coefficient, but notice the x is not inside, and it doesn't matter what the coefficients are. Up here, all it says about the coefficients, they're real numbers. And so this guy is a polynomial. Specifically, we have only whole number exponents. No variables in radicals or denominators. So polynomial, yes. Denominators. And my degree, my highest exponent, let's spell degree right. My degree here would be -5. The next guy, not a polynomial. No. And really there are two reasons. The 1 over x. Let's be a little more specific here. Because we got that 1 over x, and specifically the variable in the denominator. And also, well, there are a whole bunch of reasons. The x, the -2, the negative exponent. And lastly, the square root of x, the variable in the radical. Any of those would be sufficient reason to make it not a polynomial. This one just had lots of reasons. So now we know what a polynomial looks like as far as its formula goes. We can also talk about a couple, what's the word I'm searching for? Properties, couple properties graphically. And so this next page kind of talks about some graphical properties. We have already studied the graphs of two polynomials. We've studied the x of the standard quadratic, which is the x squared, and the standard cubic, which look like that guy. Both of these functions, notice their domain is negative infinity to infinity. This goes forever left, forever right, so negative infinity to infinity. And same thing here, negative infinity to infinity, forever left, forever right. And then another thing these two graphs have in common, this will be a new phrase, their graphs are continuous. A graph is continuous when there are no gaps, breaks, or holes in the graph. And that's what it says down here. The gaps have no gaps, breaks, or holes. Such graphs are called continuous. All polynomial graphs are continuous. The graphs of all polynomials are continuous. Notice that the domain is all reals. The graphs of polynomials, because the domain of all polynomials, they will forever go left and right. And we actually talked about that domain issue of polynomials before, that the domain of polynomials were all reals. So graphically, we know that something is a polynomial when we see that the graph goes forever left, forever right. That corresponds to the domain being all reals, and the graph is continuous, no gaps, breaks, or holes. So down here we have three graphs, and the question is which one of these is continuous? Now I did get really lazy when I was making my notes. There should be arrows at all these places right here. And then what's happening on this side here is that this guy's coming up like that and running right alongside the axes there. So that's what the graph should look like. And only one of them is a polynomial. Only this guy in the middle is a polynomial. It's continuous, no gaps, breaks, or holes, and it goes forever left, forever right. This is not a polynomial because it's discontinuous. It is not continuous. Continuous graphs come in one piece. It has two pieces. Continuous graphs come in one piece. This is not a polynomial. It doesn't go forever left. It starts right there, and it doesn't go to the left forever. Which means its domain on this guy, the domain of this guy would be 0 to infinity with a square bracket on the 0. So there's another property of polynomials graphically. The graphs are continuous, no gaps, breaks, or holes. The graphs come in one piece, you could think of it, and the graphs go forever left, forever right. Now what we're going to develop over the next several problems and several pages are ways to graph these things. Now in today's technological age with calculators and whatnot, some of this information may not be as important as it was before, but I've been told to teach it, so I will teach it. But that is what we're building towards, graphing these things. And the first thing we're going to talk about as far as building these graphs is the concept of end behavior. By end behavior, we mean whether the graph rises or falls on the extreme left or extreme right sides of the graph. To determine the end behavior, we'll use the lead coefficient test. That's a little misleading, but that's what every textbook calls it. The lead coefficient test uses both the lead coefficient and the degree of the polynomial. So it isn't just the lead coefficient, it's a combination of the two things. Now, I like to call it the lead coefficient test chart, because this is really how I think of this. And again, what end behavior is going to do is it predicts the way the graph goes on either end. Here, it rises on both left and right. Here, falls both left and right. Here, falls left, rises right. Here, rises left, falls right. It tells us what's happening on either end. But it gives no prediction on the middle, but just the end. Now, like I said, it goes with its combination of two things, the degree and the lead coefficient. When we're talking about the degree, which is the highest exponent, all we care about is whether that degree is even or odd. And when we talk about the lead coefficient, the number that's in front of that degree term, whether it's positive or negative. So if I have even degree, positive coefficient. So a tiny little example would be f of x equals x squared. And this is the way I think about it. I don't memorize all these words. I think about an example. So my degree is 2. My lead coefficient, being very, very explicit, would be 1. So I have an even degree, positive coefficient. We all know that the graph of x squared looks like this. And so this tells me that my end behavior is rises left, rises right. That I just think of a tiny little example, and then that example will tell me the end behavior for everything that falls into this category of even degree, lead coefficient positive. The flip side, even degree, lead coefficient negative. So here, -1, can't really write the -1 in there, but degree even, 2, lead coefficient, -1, negative. We know that that graph is the parabola that opens down. And then based on that, what I know that graph looks like, I now know that my end behavior is falls left, falls right. And so what this is saying is that every function that has a negative lead coefficient and an even degree, every single one of them will have this end behavior, falls left, falls right. Now, all sorts of stuff can be happening in the middle, but on either end, falls left, falls right. Degree odd, lead coefficient positive, and again, very explicitly, there's a 1 there. So degree odd, 3 is an odd number, lead coefficient 1, positive. When I have that, x cubed, we all know that that's the graph of what x cubed looks like, and then we can see that the end behavior here is that it falls left, rises right. So this is telling me that any function that has any polynomial function that has an odd degree and odd degree and positive coefficient, they will all have an end behavior of falls left, rises right. Again, anything could be happening in the center, but we know that it's going to falls left, rises right. Then my last option, degree odd, lead coefficient negative. So there's my odd degree, 3, lead coefficient, -1, negative. So negative coefficient, odd degree. There's what a little example graph would look like, and that rises left, falls right. So again, it's saying that every single function that falls in this category, every polynomial function that falls in this category of an odd degree and a negative lead coefficient will have this end behavior. So let's do a couple problems here. Use the lead coefficient test to determine the end behavior of the graph of the given polynomial functions. And again, I don't memorize these words. I give myself a little example. My degree is 5. And what I care about that is it's odd. My lead coefficient is -2. And what I care about is that it's negative. I don't really care about the 2 part. I care about the negative part. And so my example there that I think to myself would be f of x equals -x cubed. Because I know what that looks like. That's something I'm familiar with. -x cubed looks like that. So then I draw myself a little thing. And so my end behavior, I'll write it up here, is rises left, falls right. And really, this is all my thought process. You know, come test time or whatnot, if it's a regular paper and pencil test, you're really just thinking all that because you can visualize this. That I think, okay, here's a little example that I can think of, then I can see this in my mind, which then tells me rises left, falls right. And we'll end this video and pick up with more end behavior on the next one.